Welcome to lecture number 52, advanced topics. So, the last class I talked about deadlocks, right? So, here I'll start with deadlocks, causes and prevention. So, what do you mean by deadlock? So, I gave a physical example. Suppose I mean in a track, the two trains, right? They are facing each other, right? Assume that no accident is happening, but they are facing each other by somehow. Let us say due to signal failure or so, right? So, in that case, how do you right overcome this, or even before, how do you prevent this? So, here, right, so in the programming point of view, right, so deadlock, so this occurs when two or more threads. So, here I will talk in terms of thread, right. So, they wait indefinitely, right. So, they wait indefinitely for each other to release the resources, right, almost the same meaning, right. So, this causes circular wait, right. So, this causes circular wait. What do you mean by circular wait? So, the threads waiting for resources held by each other, right. So, this is called as a circular wait. Another one is hold and wait, right. So, threads which are holding resources while waiting for others, right. So, these are all the causes made by the deadlock. One is a circular wait, another one is hold and wait, right. So, how do you prevent this? So, we have to use a consistent locking order, right. So, when you use the consistent locking order, we can prevent. So, the deadlock can be avoided by holding locks while waiting for other resources, or we can use timeout based locking mechanisms, right. So, this is about your deadlock. We will talk about thread pooling in Java, right. So, what do you mean by thread pooling? A pool of pre-created threads, right. So, pool of pre-created threads ready to perform the task, right. So, this thread pooling reduces overhead by reusing the threads, and we are going to use this executor service, right. In the Java utility, let us use the executor service. So, we will take an example with the executor service, and then we will use executors as well, right. So, here you go, public class thread pool example, right. So, let us consider the class, it is a driver class thread pool example. So, here you have the main program, correct. So, here you have the main program, and executor is an object under executor service, right. So, your executors is invoking new fixed thread pool. So, here it can hold up to 3 threaded pools, right. So, 3 pre-created threaded pools, that is what the meaning, right. So, here you have 3 threaded pools. So, now for I is equal to 1, I less than or equal to 5, I plus plus, right. So, 3 threaded pools for loop, and task ID is I. So, now you have a lambda expression here, it is calling the execute, and it is a lambda expression. So, now you have system.out.println the task, right. So, 3 threaded pools are there, that is what line number 6 is saying, right. So, task ID you are printing, and the thread which is calling the get name under the current thread. Okay. So, this is going on, this lambda expression is going on, right. So, then once it is printing, executor is invoking shutdown, right, executor is invoking shutdown. So, if I run the code, right, so I will get, so I said how many threads, how many threaded pools, 3, right, how many threaded pools, 3, right. So, you can see thread 3 2 1 and again 3 2, right, something like that. So, here you can see the task ID. So, need not be 1 2 3 4 5, this we had seen previously also, right. So, it is starting with 3 and 2 1 randomly 4 5, right, but totally you have I is equal to 1, I less than or equal to 5, I plus plus, right. So, what we can do, we will run this code in Java. So, let us go to the Java compiler, you can see the output. Okay. So, the I said 3, right. So, the 3 threaded pools, right. So, if you look at the output, the 3 2 1, right. So, again 2 3. So, it is like a slightly a different output, we are not getting 1 like what we used to get here, right. So, yeah, you have to get like this, right. So, here you can see the thread, you can see 3 2 1, right. So, here you have 3 2 2 1 3, whereas I projected here 3 2 1 3 2, yes, it is possible, right, and the ID is also 1 2 3 4 5, all are covering in a different way, right. So, you have 3 first, task 3 first, then 2 5 1 4, all right. So, this is how the threaded pool concept is working in Java. So, now let us consider two classes, right, async and future in C++, right, asynchronization. So, asynchronization, async, it is launching a task asynchronously, alright, and the future, the class future, which is retrieving the result of an asynchronous task. Let us see an example. So, let us include future, right, let us include the header file future along with IOStream, right. So, now you have compute square, right, the function compute square, alright. So, which is returning x squared, which is not a problem. Let us go to the main program. So, main program, you have an object result under the class future, future of integers, right. So, here async, which is a constructor, you are passing async compute square and 5, right. So, in fact, we have seen the similar meaning, it is nothing but when the result is invoking, right, when the result is invoking get under future, it will call compute square by passing x 5. So, now see out square you put, the result is invoking get, right, the result is invoking get, that means you are passing compute square and 5 over here in the constructor of async. So, what is happening over here, x is what now, x is 5. So, that means return x squared. So, 5 into 5, 25 will be returned. So, we should get the output square is 25, right. So, when I run the code, I have to get the output square, right, colon, I am expecting this, that will be printed, and once the function result dot get is invoking. So, async, you are passing compute square and 5, correct. So, compute square is nothing but a function in line number 4, that means 5 you are passing, x will take the value 5 and x into x is x squared. So, square is 25. So, this will be printed. So, can you just work it out, and yes, what I will do, I think first time we are running C++, right. So, we will run, I will run C++. I thought of you will work, what we can do, we will work it out. Dev C++ or here it is command prompt, we can G I will do. Yeah. Yes, you can see the output square is 25. So, compilation and run the code in the command prompt, right. So, you are getting square 25. Okay, I hope it is clear. So, the next concept, semaphores, right, using semaphores in C++. So, semaphore, which is controlling access to a shared resource with limited capacity, right. So, here what we can do, so we can use counting semaphore, right. So, we can include semaphore like what we have done in line number 3, right, and here you have the initialization, right, line number 5 you have the initialization, which is nothing but counting a semaphore, right. So, which is initialized with a capacity of 3, right. So, the meaning is it can allow up to 3 threads to proceed at a time, right. So, let us see how the worker function is doing, right. So, here you have the worker function, right. So, the worker function which is acquiring the semaphore, and here you have printing the message worker, right, with worker ID, right, is running, right. So, here you have this underscore thread. So, under this you have sleep underscore for, right. So, that means this will sleep for 2 seconds, right. So, this will sleep for 2 seconds and then releases the semaphore. This is what exactly the work function goes, right. So, let us go to the main program. In the main program you have 4 threads, right. So, the total capacity is 3, you have 4 threads, the threads are nothing but T1, T2, T3 and T4, right. So, each calling the worker function with the different ID, right. So, everyone is calling the worker function with the different ID. The main thread waits for all worker threads to finish using join. So, T1, T2, in fact, we had seen this example, only one time we use, 2 times we use, if you recall. So, here the main thread that waits for all worker threads to finish using join, right. So, here the semaphore ensures that only 3 worker threads, right. So, that can be executed the critical section, right. So, which can execute the critical section, right. So, printing the message and sleeping at a time. Once a thread finishes its critical section, it releases a semaphore allowing another waiting thread to proceed, right. So, that is what exactly it is happening, right. So, this regulates the number of threads accessing the shared resource and prevents race conditions, right. So, in the console output. So, in this case, so the program that you had seen, the mutual exclusion is not guaranteed. So, here the mutual exclusion is not possible, right. So, the multiple threads that you are seeing over here may try to write in one go, as you can see in the output, right. So, suppose if I run the code, I mean here you go, here you are see. So, this is the output, right. So, multiple threads you are seeing may try to write in one go, as you can see in this output, right. So, but this is depending on the underlying resources also, right. So, what how we can fix this? So, we can fix this using the mutex. So, that we are going to see. So, before that what we can do, we can run this code in C++, right. So, we can run this code in C++. Yeah. So, here you go, all right. So, here you are, yeah, that is what I said, right. The mutual exclusion is not guaranteed, but here it is coming. So, it depends. So, sometimes you may get the output what I had told in the slide, right. So, sometimes you may get like this also. So, it is possible, but suppose you are getting like this, what we had seen over here, right. Suppose you are getting like this. So, in that case what we can do, right. So, we are going to use, suppose, right, I am running the code, there is a possibility, right. So, it is depending on the resources, right. Suppose you are getting the output like this. So, this problem can be solved, right. We are going to see in the next slide using mutex. So, now we will use semaphores with mutex. So, whatever problem that we had seen in the previous slide. So, when I include mutex, right, or semaphores with mutex, right, almost the same program. So, what we can do, we can use the same code, semaphore of 3, right, and a worker function, so which is acquiring, right. So, here you can have this lock, right. So, under lock, right. So, you are passing lock underscore mutex. So, in fact, mutex we have studied, right, under the class lock guard of mutex, right. So, now you try to print this worker ID and is running, right. So, rest are all same. So, sleep for 3 seconds and then it will release, alright. So, you are having 4 threads and then the join you are calling, rest are all same, only line number 12 we are including, that means lock function you are passing cout underscore mutex under lock underscore guard, right. So, now when I run the code, right, so I have to get the output like this, right. The ID can be changed, right, it need not be 1 2 3 4. So, you can get like this also, right. So, in the previous example, previous, right, previous only semaphores, right. So, there is a problem, it is all depending on your CPU, all right. So, the one we have run right now, I mean the previously, I mean you have got, all right. So, this is all, I mean depending on your CPU. So, in this case, so semaphore with mutex, so you will always get like this, okay. So, in the previous example, there is a possibility that you may get like this, you are seeing worker, 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 one is running, yeah, you may get, right. So, you can keep on running this, right, because in our case, so sometimes it will work fine also, right. But to avoid this problem, we are using the mutex, and when we are running the code, we will get the output like this. So, what we can do, we will run the code in C++, right. So, you can see over here, right, we are getting the output. In fact, here it is giving 1 2 3 4, right, semaphore with mutex, right, the previous one 1 2 3 4. So, now what I will do, semaphore with mutex. So, that is you are getting perfectly, right. So, there is a possibility that both will work and give the same output, possible, right. It is all, I mean how your CPU is using the resources, correct. But sometimes what happens, so whatever the output that we got in the previous slide, so there is a possibility, right. So, you may get like this. So, you can try, only thing you have to try, right. So, you may get like this. So, this problem will be solved, in fact we had seen also. So, we are getting the output like this. So, this is semaphores with mutex. So, let us consider with the Java, right. So, semaphores in C++ we had seen. So, now we consider semaphores with, I mean in Java, right. So, here we are including the utility semaphore, right, concurrent dot semaphore. So, let us take the class semaphore example, right. So, here I have an object semaphore small s, under the class semaphore, right. So, dynamically allocated the memory with the constructor semaphore, and as usual, right. So, you have 3, right. So, 3 threads are running, right. So, 3 resources, right. So, now let us have the lambda expression runnable worker equal to. So, similar we have used in C++ also, right. So, you are trying to acquire, the semaphore is trying to acquiring, all right. So, almost the same. So, here you have get name under thread, right. So, which is available in current thread, right, is running will be printed. So, which thread will is running, let us say thread 1 identifier, and thread dot sleep for 2000 milliseconds. So, that means 2 seconds it will sleep, same, right. So, here you are putting 2000 because of the milliseconds and try. So, if there is any exception, it will be caught over here, it will be calling the print stack trace, and finally, right. So, it will be releasing, that semaphore will call the release, exactly what we have done in C++. So, here it is equivalent in Java. So, now for loop I is equal to 0, I less than 5, I plus plus, the thread, right, we are passing worker, the worker will invoke start, right, the worker will invoke start, exactly same what we have done, right. So, that means it will acquire and then it will try to print and then it will sleep for 2 seconds, right. Finally, it will be released, right. So, here you will get the output like this, right. So, you may get the different ID thread 0, 3, 1, 4, 2, and you can see they are running, right. So, at a time you have 3 resources, that is what line number 5 is suggesting. So, what we can do, we will run the code in Java. So, I use Java compiler, yes, you can see, all right. So, 2, 1, 0, 3, 4, because we are run the loop from 0 to 4 if you recall, right. So, that is why we are getting output like this, right. So, here you have 0, 3, 1, 4, 2, and yeah, you may get any other order also. So, here when we are running 2, 1, 0, 3, 4, okay. So, this is how the semaphore works in Java. So, both C++ and Java. So, now, so what my advice is, you practice these codes. So, in fact, in C++ we had seen semaphore with mutex also, correct. So, these are all the programs you can practice. So, let us see the next concept, thread safe data structures, right. So, to prevent the race conditions, we have already seen mutex, right. So, now using synchronized or lock based data structures, right. So, we are going to see, right, how this is working, right. So, that is you call it as a thread safe data structures. So, in C++, the common thread safe data structures we have already seen mutex, all right. So, apart from mutex, we can also see atomic, right, and in the Java concurrent hash map and copy on write array list, right. So, these are all the synchronized or the lock based data structures. So, these are all the common thread safe data structures. So, let us consider in Java, right. So, you include the utility concurrent hash map, all right. When you include the concurrent hash map. So, here public class, you have name of the class is thread safe map, right. So, here you have main, therefore, it is the driver class, correct. So, here you have an object map under concurrent hash map. So, that is what I said previously, right, concurrent hash map. So, which has integer and string, and in the right hand side you have dynamically allocated a memory with a concurrent hash map constructor, okay. So, let us have the map, the object map which is invoking put. So, one is the key, another one is a value. Your key is one map, right, we have seen map data structure, right. So, put map is invoking put, right, 1 comma a, 1 is the key and a is the value. Similarly, 2 and b, right. So, now the map is invoking for each, for every, right. So, key and value, right, for each key and value with the help of arrow operator system dot out dot println. So, it is going to print key and value, right. So, what are all the key and value are there, 1 and 2, right. So, 1 and 2 are nothing but the keys, the corresponding value should also be printed when you are calling this, right. So, these both will be printed. So, when I run the code, I have to get the output 1 colon, right. So, that is what key 1 colon value A for first, and then again, right. So, 2 B, which will also be printed, right. So, this we will see in Java, right. So, let us go to the Java compiler, we will run the code. Yes, here when you run the code, you can see the output, right, 1 colon A, 2 colon B. So, thread safe data structures, this is an example. So, in terms of Java, I explained this. So, the common thread safe data structures in C++, mutex already we had seen, you can also work it out with atomic, and in the case of Java, you can see this example using concurrent hash map, right. So, you can also think of using, you can try this copy on write array list. So, let us consider this case, right. What is the difference between parallelism and concurrency, right. So, in the concurrency, the multiple tasks make progress by sharing resources, this is what we studied, right, the concurrent, and several examples we have seen, right. Also, the concurrency focuses on task switching. So, you are getting 0, 1, 2, 3 or sometimes 1, 2, 0, right. So, this is concurrency. So, then what do you mean by parallelism? So, parallel, right, I am calling it as a parallel program. So, the tasks run simultaneously on multiple cores, right. So, nowadays you are getting a multiple core machine, right. So, the tasks which run simultaneously, that is a keyword, on multiple cores. So, parallelism which requires hardware support for multiple core execution, right. So, whereas concurrency, this is enabling responsiveness, and parallelism is improving the speed. Suppose you have the parallel machine and then assume that you are running the program, right. If you assume that you are using a single machine, all right. So, your speed will be improving, right. Whereas, in the case of a concurrency, this is enabling the responsiveness. So, this is a major difference between the parallelism and the concurrency. And when I am talking about multi-threading, right. So, in real time examples, so you can have the web servers, right. So, the web servers can handle multiple client requests, game development, right. So, when you have a rendering or AI or physics, right, when you want to develop some games, so you can have the separate threads, right. So, separate threads for AI, separate threads for physics, rendering, all right. And another application is the data processing, all right. So, this performs the parallel computations on large data sets. Suppose I want to, right, read the satellite image file, all right. So, which is a very hot task, right, it is hyperspectral or a multispectral image, and I require the parallel computations, or even I want to do some, let us say, image processing, right, image processing algorithm on the satellite images. So, these kind of applications the parallel computations require, all right. So, the next one is a multimedia applications. Suppose you want to play audio or render video, right, or you want to select some frames, keyframes, or you want to do some action recognition in the video, right, and manage user input, right. So, these are all happening concurrently, okay. So, play audio, render video and manage user input concurrently. So, these are all under the multimedia applications. So, these are all the real time applications. So, now the next one is best practices for multi-threading, right. So, you minimize shared state to reduce race conditions, right. So, you have to minimize shared state, therefore, we can reduce the race conditions, and we use thread safe data structures. So, this we had seen, this also we had seen, all right. And for multi-threading, right, so we have to avoid deadlocks by careful lock ordering. This also, right, we had seen with an example and I also told, right. So, you have to prefer thread pools to avoid excessive thread creation, and we have to test extensively to catch concurrency related bugs, right. So, these are all the best practices for multi-threading. So, I will summarize the multi-threading concepts, right. So, the multi-threading enables concurrent execution in programs. So, we have covered these topics, right. So, we have talked about thread pooling, synchronization, asynchronization, semaphores with mutex, right. So, we also talked about thread safe data structures, and then we had seen the difference between parallelism and concurrency, right. So, the advice is you have to choose the appropriate strategies to balance the performance and the correctness, right. So, with this the multi-threading concepts is over. So, in the next class I will talk about the network programming. Thank you very much.